So what happens when I make a measurement on a quantum system? Well, first of all, each measurement is associated with a particular Hermitian operator called an observable. Now, each observable is Hermitian, which means it has real eigenvalues. So those eigenstates form a complete orthonormal basis, and we can write the observable operator in terms of those eigenstates. So if I apply this to one of these states OJ, I'm just going to get the lambda j out. So this is the eigenvalue, and these are the eigenstates. Now, because these OJs form a complete orthonormal basis, then I can always write any state that I have before I make my measurement in terms of them. And I'd just like to note that here, as in other places, if I write a sum and I actually have a continuous index, I can always just turn that into an integral. So I have a very relaxed attitude between switching between sums and integrals. They're all just sums over our vector space. So we expand our state in terms of the eigenstates of our observable. And then if we make a measurement associated with this observable, then what happens is this state changes dramatically. It jumps to one of these eigenstates. So in fact, what we get is not a deterministic result, but in fact a stochastic result. So the only thing that the probability of going to a particular eigenstate can depend on is the coefficient of that eigenstate in the original expansion of our state. And it can't just be the coefficient itself, because that's a complex number. It must in fact be the mod of the coefficient. And because all the probabilities have to add up to 1, it is in fact mod squared, because our state is normalized. And so we have different probabilities of going to our different eigenstates. And if we land at a particular eigenstate, then we say that the measurement gave us a result of that eigenvalue. And because if we measure a particular value for our measurement, if we then measure it again, we should get a consistent value. So then our state must have jumped to that eigenstate. So those are the three postulates of quantum mechanics. The first is that all physical systems are described by elements of a Hilbert space. And we haven't discussed some of the other key Hilbert spaces, for example, the harmonic oscillator. So if my Hamiltonian for a particle was, then the eigenstates of that Hamiltonian are indexed by a natural number n, where n goes from 0 up to infinity. And indeed, the best way to write this kind of Hamiltonian, the best way to deal with these kinds of systems, these harmonic oscillator systems, is using ladder operators, which raise and lower the number states. And if you do that, then you can write your Hamiltonian in terms of the ladder operators like that. The reason that harmonic oscillators are such an important quantum system to look at is that in fact all bosonic fields, half of all the particles in the world, have that kind of structure in their Hilbert space. So once we've got a handle on all the different kinds of Hilbert spaces that describe all the different kinds of physical systems, we need to look at the evolution. Now we talked about the evolution in terms of the Schrödinger equation, which is very specifically in terms of the Schrödinger picture. So the Schrödinger picture says that states evolve in time. But in fact, that's not the only way to look at quantum mechanics. What we really need is all our predictions to evolve correctly. Our predictions can be encoded in terms of the expectation values of any operator. And so in the Schrödinger picture, we look at this and we say, look, there is the state as a function of time. But there's actually an alternative formulation of quantum mechanics where the states don't evolve in time and the operators do. And if we look at this expectation value equation here, we could easily have grouped these terms together and decided that instead of these states evolving in time like this, in fact these operators evolved in time like that. So now you have time-dependent operators, and these are known as operators in the Heisenberg picture. And sometimes calculations are easier in the Schrödinger picture, or sometimes they're easier in the Heisenberg picture, and so we do occasionally swap from one to the other. And indeed, there's also the interaction picture where you put some of your evolution in the states and some of your evolution into the operators. Now, of the three postulates, Hilbert spaces, evolution, and measurement, measurement is probably the most mysterious one. Measurements can have serious consequences. For example, if you measure a system really often, you can actually change its behavior dramatically. An extreme example of that is the quantum Zeno effect, where measuring a system that can couple between two states sufficiently often actually stops that system from coupling between those two states. Also, this measurement postulate talks about making a very clear, perfect measurement of some observable, of some quantity. What if your measurement doesn't discriminate between everything? What if you are only measuring, say, the parity of a system? So you might be trying to measure a wave function, and instead of measuring its position or its momentum, you might be just measuring whether it's on the left or the right. How does that work? How do we work out what happens in that case? What happens if your measurement has some kind of error? What if there's some kind of uncertainty in your measurement? In other words, rather than making this perfect measurement, what if it's a weaker, more suggestive measurement? What if you become more convinced that it's on the right, rather than entirely convinced it's on the right? And to model subtle things about those kinds of measurements, and indeed almost anything else with real physical systems, we need to be able to handle more than one system. We need to be able to talk about the system and the measurement device. We need to be able to talk about correlations between things. In other words, in order to deal with quantum mechanics in the real world, we really need to be able to deal with the quantum mechanics of more than one system. Nearly all our physics has been dealing with more than one thing, and we have to do that with our quantum mechanics as well.